Okay, now let's start. Thank you everybody for joining. I think this might be one of the less serious talks, but not totally off the wall. Like, this is still a protein modeling project with machine learning. It's just going through the scenic route of how you can go about training neural networks. So, as the title says, there's this video game that I work with that just turns out when you represent it as tensors, it can be represented the same way that we represent protein residues. And so I try and use the video game to quickly learn so that I don't have to slowly learn with protein. I'll get in more detail with that, but that's in case I just talk about a video game and people wonder why. This will wrap back to proteins. My name is Jack. I'm a senior machine learning scientist at Menton AI. I am a recent Rosetta grad from Brian Coleman's lab at UNC. And this project actually spans both of these, and more. Like, I've been working with this game for a good while. So I am at Menton now, but this isn't necessarily a Menton project. I do work with graph convolutional neural networks nearly exclusively nowadays, but not necessarily. And for the scope of this talk, I think really the only point to share about graph convolutions is that instead of representing data, in a grid or as voxels, both, as neural network input and or output and anywhere in between, our data is a series of nodes and then edges connecting the nodes. And both the nodes and or the edges can have attributes associated with them, which I usually try to point out because it isn't always assumed. In some fields, an edge is just there or it's not. But for us, there actually is data on edges that we want to learn from. To get into a little bit more detail, I'd like to just share quickly how we represent proteins as graphs. And I'm using a little cyclic peptide here, just, the fewer residues, the easier it is to draw. But here we have an 8 residue cycle, and I've colored it such that each residue in this cycle is a different color in the rainbow. When we represent this as a graph, each residue has its own node or vertex in the graph. If you haven't worked with graphs before, this is just, a graph is just a series of nodes with edges or lines connecting them. I don't know if that clarified. In Facebook, each node is a human or a user, and then there's an edge connecting Facebook users that are Facebook friends. But that edge itself might have attributes like how long they've been friends or how often they interact. For us, proteins, each residue is a node, and then we draw edges in between residues that are polymer bonded, so this is a cyclic peptide, so there's no termini. But we can draw edges between anything you'd like. What I tend to do is draw edges between any two residues that are either polymer bonded or close enough in space to interact with one another. So for example, this green and this blue, if you just twist the side chains, they might clash. So there should be an edge. Well, I guess I didn't draw one. Bad example. There would be an edge between this node and this node if I wanted to model that potential interaction. That's the gist. The node tensors themselves, or the attributes, contain information on those residues, so backbone torsion angles, sidechain identity or sequence identity, which amino acid it is. Sidechain torsion angles, really just one body terms as we think of it in the Rosetta score function. And then the edges are the two body terms as we think about it, or residue pair interactions. What I really like to do is, again, trying to stick with the Rosetta vocabulary, but there's a lot of different words for this, is a kinematic jump. So for every residue, you can use your sidechain, or rather your backbone atoms, to define a coordinate frame. And then when you have two residues floating in space, you can measure the transformation between their two coordinate frames. And so this says, this is more than just giving distances and angles how TR Rosetta does. This is, the entire transformation from going from one to the other. And I partially regret saying that this is more than what TR Rosetta does, because I think you can generally calculate this from TR Rosetta's angles and distances. But this is a little bit more backbone oriented than section oriented. I suppose if I take a step back, you can choose either method. I've tested both. The general broad strokes point that I'm trying to get across is that the edges represent residue pair relationships. And this includes, even though I didn't list it here, things like, are we polymer bonded? Are we disulfide bonded? And interactions like that. This could be its own talk too, but just the way that the neural network itself is strung together. When you want to represent a graph as tensors, it walks around town as 3 different tensors that are all packaged together, and the nodes and their attributes are listed in the X tensor. This is the convention naming. X is the node attributes. A is the adjacency matrix, so it just says where edges exist, but E contains the actual attributes on these edges. You input X, A, and E into the model. You run graph convolutional layers, which most of them only update X. We actually recently published one that updates E as well. So I'm just going to broadly say that X and or E get updated. And you will run a few different convolutions, and then your output is X or E. A generally doesn't get updated unless you do some sort of clustering, which is outside the scope of this. I generally don't do that so much. The convolutions themselves, again, I'll try and skim the surface, but that might hit no man's land between being unsatisfactory and confusing. Graph convolutions are often called message passing. This is a common flavor where within one convolutional layer, you would iterate over every edge. And then let's say this is edge from node I to node J. You would concatenate the node attributes of I, the node attributes of J, the edge attributes from I to J, and if there's an edge in the reverse direction, you would also add the edge attributes from J to I. I mentioned earlier that the edge data might be a coordinate frame transformation. The other edge would just be the transformation going the other direction. If you're measuring just distances, these would be redundant, but often we do more advanced operations. Concatenate all these together, you run them through one or more dense layers, and then this creates a message which pertains to this specific edge that was used to create the message. There's then a round of propagation, which I think is broadly just you take a node. I say I think because this differs from implementation to implementation, but the most common one is you just take all of the messages. So there's one message per edge. For a single node, you take all of the messages adjacent to it and you just sum them together. This kind of struck me as inelegant at first, but the beauty of just summing them together is you get order invariance. So when we list our nodes and edges, it doesn't matter the order that we list them, which is really important for us because we want, it doesn't matter if, this is node number 1 and this is node number 2, or if this is node number 1 and this is 2, and your work, it doesn't matter where you start counting, and we shouldn't care where we start counting. So order invariance is very important for us. And this message passing algorithm maintains that for us. So that was just an unsatisfactory but quick summary of the actual tensor operations that we're playing with. really just to set the scene, because I'm going to try and draw a connection between how we perform this level of setup between robots, this video game I play with, and proteins. And so just to take a complete left turn, we're going to merge again, but I'd like to talk about this game a little bit. And the motivation here, I'm going to have another level of like surface level distraction. This is Batman kicking a field goal in American football. For those who aren't familiar, just in American football, if you have your ball and you kick it through these uprights, you can get points for the game. There are two variants. There's a 1-point field goal where you're very close generally to the uprights. And then there's a 3-pointer, which is farther away in general. They occur at different points in the game, so I'm speaking generally. But a few years ago, the Football League made the 1-point attempt more challenging by moving it farther away from the uprights. And an interesting effect of this is that the 3-point success rate decreased, even though the 3-point attempt was unchanged. It's still kind of a current mystery because this was just done a few years ago, but analysts are saying that the players really need the 1-point attempts to be relatively easy so that they can iron out their technique. And, if you're only doing the challenging attempts, you can't like grow, or you can't maintain your skill as easily. It really helps to have a few easy attempts filtered in. And the data reflects that. And so what I'm trying to do with this project is, between my big protein machine learning projects, which are the 3-pointers, how can I keep a healthy diet of the 1-point attempts where I can learn new things and it'll probably succeed anyway, but keep up the repetitions and be like Batman here. Sorry, I just really wanted that Batman gift, so maybe that was a stretch to include that. Sergey says, you mean you can use soccer moves in football? Yes, though soccer, it's a little, there's no goalie flying in the sky. But yeah, so this is the board for robots. This is, I guess I should give proper credit. I first came across this in the form of new robots, like GNU robots. But there's several variants. I believe it's decades old, with the original name being called Chase. What we're seeing now is just my own hand-rolled like GUI for it. But you are a human. At the moment, you're right here in the middle of the board. And there's several other elements scattered around. And they're all robots, and they're chasing you. And if they catch you, you're dead and the game's over. And your goal is to kill all of them before they kill you. You can move. This is a turn-based game. You can move in any of the 9 immediate boxes. So up, left, up, right, stay put. Really, this 3x3 is your move set. And once you make a move, every robot on the board takes a deterministic move towards you. So say you're human and you make this move, then you can calculate, essentially every robot just takes a step in your direction. It's not terribly complicated. It's, if you think of it as X and Y, if your Y is greater than the robot's Y, then they'll take a step in the Y direction. And if your X is greater than the robot's X, they'll take a step in the X direction. And if both are true, then they'll take that positive diagonal. So for example, when we move here, then each robot will move towards us. So if we take a look at this guy, he'll move here. I'll keep my mouse there for context. And he does. And so they close in on you and really quickly. So you have to move strategically. And your goal, your means of killing them is to make them walk into each other and explode. So for example, this is a different board, but now your human is on the bottom right here. And if you move here, then we can deterministically figure out that each of the other robots up here will all move to the same space. And upon doing so, they will create an explosion. They will, if you have two or more that occupy the same space, that's an explosion. The explosion persists, and now the human can walk up here, hide behind the explosion, and then all future robots on this board, let's see, this one will walk diagonally down the gray. They'll all walk into this explosion, and you're safe. There's a few more nuances to this, but broadly, this is the idea. And this is just iteration of analyzing your environment and choosing a direction to go in, causing other elements around you to interact with one another. I'm happy to answer questions about this. There aren't a ton of rules here, but let's see, chat. Superman for the goalie from America. Was that ding dong a hand, or was that someone entering? I don't think I see. I'll just keep moving along, but please, anyone interrupt. There's only 12 of us, so when feel free. So back at UNC, I thought that this mapped really well to a CNN because it's a grid. Essentially, you could just
actually, can I ask one question?
Yes.
So if I understood, are the rules always going to be the same for all the blue dots, and then are you trying to predict H, or is it the other way around? You're trying to make the blue dots smarter?
Oh, good point. The blue dots are entirely deterministic, and then you are controlling H, the human. So ideally, H is what you can make smarter or dumber. It's really the only thing that you have control over. Pardon me. Did that answer?
Yep. Thank you.
Back in grad school, I thought, I was just learning machine learning, and I was a big fan of this game already at the time. So I figured this would be a good mapping to a CNN because it's just a grid. And you could, just make this such that, each element on the grid is a pixel, and just run this through a few layers of CNN and use that to predict your outcome. It didn't succeed, but I don't think that's the CNN's fault. I was really new at machine learning at the time, and I'm open to the idea that CNNs can still do a good job at this. I should also say that I have a slide later on this, but I put this out of order, I suppose. My attempt was to log my own moves playing this game and to train a CNN that will take a board and just predict what move I would do. Which is, it's not perfect, but it's the easiest way. I wasn't prepared for reinforcement learning or anything where you learn how to play the game on your own. Since going to Menton, I've really tried to do as much with GE graph convolutions as I could. And so my current approach is to represent the board as a graph. And the particular graph on the screen is just something I drew in PowerPoint. The edges are still, the rules are to be determined, but the general idea is that, you don't really waste your time looking at empty cells. You just place edges between nodes that are within a certain distance cutoff, where a node is a robot or a human or an explosion. And just learn this way, which might potentially be more efficient representation of the data. That's to be determined. But what was more important for me and how I could justify doing this in my job isn't that this is a better way to play robots. I still don't make that claim. It's just the fact that we can represent our data the same way that we do when we represent proteins. And so if we can just, if this is our 1-point field goal, then when we go back to our 3-point field goal with proteins, maybe we'll learn something from the 1-pointers and, learn better convolutions or better practices on something that we could iterate on much more quickly. I did sneak this in. There's no good point in the slides for this, but I did kind of share this because this game is really the one thing that transcends my whole career. So I went to college, University of Rochester, but I did my summer research at Michigan State every summer, and that's where I found the game. And I would go back to school and I reverse engineer and program the game. And then go to grad school at UNC. I did the CNN attempt. I reprogrammed it again in a better language. And then now I'm at Menton and I'm doing the GNN attempts. Who knows what's next, but I just, maybe this is just for my own benefit, but it's kind of fun. This is the one thing I have in my career that's really transcended back to undergrad. So it's really nice that I can tie this to proteins. But the training process, like I mentioned verbally.
Pooja has a question.
Oh yeah, Pooja.
Yeah, she's asking, is this a 2D model on a surface? Like
Exactly, yes.
dots moving on a grid?
Oops, that is the wrong button. It is. So this is it's just a larger chessboard, but yes, you can move left, right, up, down, just on a grid. Yes, that's on a chessboard. We have conceptualized if we want to do 3D robots, and I'll credit Marion Fisher from the Myler lab for that idea. She's now at Menton, and it's harder to play by eye, but in theory you can do this in 3 dimensions. But yeah, no, this is just a 2-dimensional game. So like I mentioned before, nodes, human, robot, or explosion. And then the edges, similar to how we do protein edges, we're just doing relative geometry here. So this is a little bit contrived for the sake of making this similar to proteins, but I do coordinate frame transformations, so translations and rotations. Rotations doesn't make a ton of sense because there's no orientation to these nodes. But for the purpose of contriving this for the sake of similarity to proteins, I assign an orientation. So robots are facing the human and the human is facing the center of the board, just so that I can say, this human, or rather, let's say this robot is facing this direction. So when we create this edge attribute, we can say, okay, well, this robot is roughly 30 degrees, I guess negative 30 degrees in space between the direction this robot's facing and the direction like this vector and this vector. I don't think you need that to actually learn how to play robots, but it aligns with how we work with proteins. So there are a few benefits to this. Why do we do this? It's much faster to train a GCN on a robot's board than it is on a protein. Just to give a sense of scale, a lot of what we do at Menton are very small, so 10 residue cyclic peptides. And I'm outing myself as I usually train neural networks on CPUs instead of GPUs. You can get away with it on small ones like this. But since I create my own convolutions, it makes it a little bit easier. But a protein graph with roughly 100 edges will take 4 CPUs, about 3 hours per epoch. But that's for a very small case. A robots game with 100,000 edges takes the same amount of time on 1 CPU. So for roughly the same amount of resources, slightly fewer resources, we can do a much larger graph, 1,000 times larger. And this is the scale we'll need if we want to start dealing with full, larger proteins. I should also point out that the board itself, so if you kill all the robots, you beat the level, and then you start level 2, level 3, level 4, and each one has more and more robots. So that's how we can get up to 100,000 edges. The reason that these take the same amount of time, so proteins just have more features and more attributes, it's higher dimensionality, and so that's why it would be much slower. The ability to quickly iterate on an enormous graph could help us learn, when to use each convolution. So, motivation number 1 is it's much faster. But the reason we're doing all this at all is that the results are consistent. Whatever we learn while training on a robots problem actually does translate when we learn on proteins. So this next section is just showing what we've learned from this robots GCN, and then how we've actually translated that to proteins. And a lot of the figures are going to come from this most recent paper that we just put out a few months ago, where we actually published a new convolutional layer that that just plays with proteins better than existing standards. But this layer was developed first with robots, but then we published it with proteins. So this is just all to say that this worked. But back in January, I took, and I didn't beautify this too much, but I took the robots problem, I trained it using a CNN and ECC, edge conditioned convolution, which is still the academic standard for graph convolutional neural networks that have edge attributes, as opposed to just edge exist like Boolean edges. And let's see, y-axis is the mean validation loss while training, and it is truncated for visibility. It doesn't go all the way down to 0. And so the output of the input is the board, and the output is my move that I made. And so this is just a cross entropy loss. And then CNN generally just memorizes the most common move I do. ECC does marginally better, but not that much. And then we were able to benchmark several different XCNet variants, which I don't think are worth going into the differences, but the point is just we can do many different, when we're engineering a new graph convolution, we can test many different, I'm showing the 4 finalists, but we can test many different techniques quickly and change them slightly and justify testing them again, and show that they improve. So the difference between these 2 blue ones, for example, is just a minor attention feature that we added, and they all outperform ECC, but we didn't just find one outperformer and then publish. It afforded us resources to quickly test a bunch of different variants. I'm repeating myself. The point here is just that we can have several different candidates to replace ECC. And then later, when we take XCNet, let's see, this lower blue one is the one that ended up becoming XCNet, so the lowest loss. When we use it on a protein example, so this is from the paper, which is basically looking at a protein and predicting which rotamers the packer is likely to sample. ECC, okay, unlabeled x-axis warning. The x-axis is the number of edge convolutions in the network. As you add edge convolution, as you go deeper, as you have a deeper and deeper network, ECC really fails to train. And we trained several times for each model, so that's why there's some transparency. So for 2, most of them did pretty well, but 1 failed, and then for 3, most of them did really bad. All of them did really bad. Then XCNet, yes, Pooja.
So on the previous slide, I might have missed the first couple of slides. So what is the loss? What are you training these robots on?
Just my own. When I play the game, I log my own moves. So it's just learning to play the games or play the moves. It's really predicting how would Jack play this game.
Right. So so it's trying to predict the positions, the coordinates on a 2D lattice. Yeah.
Sorry, I didn't see when people came. I should, I guess, reiterate. So the human, there's a 3x3 number of moves. Like you can go left, right, up, down, or diagonal, or stay put. So essentially there are 3 candidate moves, and then it's just a multi classification problem.
So but the classification is on escaping the robots, or the classification is on making the right moves?
Yeah, it's just making the move that I made when we logged it, which is imperfect, but
So
saying
every time you make a move that where there isn't a robot, that's a good move. Like that gives you a reward.
so this isn't reinforcement learning.
Right.
This is just we logged this board, and then did Jack move here? Did he move here? Did he move here? Did he move here? And so on for all 9. And so at the moment, the loss function is just, can you predict which of these 9 that Jack moved to, just as a classification problem.
Okay, I see. And then you think this kind of data works well for proteins because maybe there is some non-overlap that the network can learn, or I'm trying to understand, why does this transfer well to proteins, or why does something that works in this would also work on proteins?
Sure. The trained network itself, I don't think is useful for proteins. It's
Yeah.
the hyperparameter and really the user being able to learn the correct hyperparameters.
Have you tried randomly choosing the hyperparameters and seeing if that works just as well?
Well, this is no, I haven't.
Okay.
I think one of the motivations for me is that protein neural network training models can be expensive enough where you can't try hundreds of different hyperparameters. Where this you can. For the production line, we'll train in maybe 5 models per attempt, but we'll only do at most 10 different attempts. Otherwise, that starts to get a little costly.
Right. I see.
So really,
I'm just trying to get an intuitive sense of when you're playing the game, how are what that grid looks like in terms of the hyperparameter space. When you zero in on the right set of parameters, I'm just trying to get a sense of what is the model learning. But so what are your hyperparameters in this case?
Let's see. So this is back when we were actually trying to engineer a new convolution. And so we were trying to think, well, where do we put the attention mechanism? Do we, once we have a message, so plan A is like, when you aggregate the messages, do you apply attention to the messages? And that was the winner. But we were trying to see, well, do we also add attention within a single message construction, or how many layers do you need when you're actually constructing messages? Is it better to have more message passing rounds or fewer rounds but more layers? Like, do you have fewer advanced messages, or do you have more simple messages? And along that line.
Yeah, I think I understand. Great, thank you.
We also really wanted to test, can you just liberally apply edges wherever you like, and allow the attention mechanism to control that for you, which ended up working for us.
One more question. So did you play with can you change the number of robots in this game? Can you make it really crowded?
Yeah, you can. In fact, so by the time, let's say we beat this level 2 is going to have, the number of robots is 10 times the level number. So the highest level you can get to is 66. So you have 660 robots. So this gets very populated.
I wonder if the density starts to match that of the core of proteins, if the transfer becomes, like if there is a chance that you could do transfer learning.
Yeah, actually, that's what I'm seeing transfer learning in the chat. So Sergey is saying, oh, well, this is a little different. I like that. Okay. Once done training, can you do transfer learning to predict what Jack would do in other situations? Which is amazing. Um, so I was thinking the other type of transfer learning. Then Bargene asks, could this be extended to fold it, where it can learn from people's moves when they play fold it? Which I think is amazing. Yeah, I think Rocco, I think we might have talked about, I know it's several people have talked about this in the past. I've never really been on the inner loop or inner circle of any of those discussions, but I think so. That is one reason I wanted to put 2D in the title of this though, because I didn't want to like oversell like this is folded. Sorry, I'm getting used to my mouse.
So I think the issue with folded is as far as representing the problem space. So I think for the robots, one of the things is the fact that, you know, sort of everything that you need to know about the game is sort of encoded in the board itself. And so I think, you know, for folded, you know, it might be a little bit different. I guess that's the question of, you know, for Jack, as far as extending this to proteins and all of that sort of thing. But it could very well be as far as, you know, picking the move that expert players do would potentially be an issue. I guess that's a question of, as far as, you know, what's your reference as far as what's the best move to go.
Yeah, that's a great distinction, because there's no reason to think the best move is the move that Jack did in this game. I think the goal that I had was, can you quickly get to a good place in parameter space? So training to predict a human's move can get you close to optimal, and then hand it over to reinforcement learning to slowly sample once you're already close. So maybe that can be done with folded as well. Rocco, for folded, would it be accurate to represent a current state of the game as a pose, like as a protein? Or is there additional or lacking information that would be missed out on?
There's some additional information. For example, like we have, you know, rubber bands, which are constraints. And so a lot of times the moves that the players are doing are imposing, you know, sort of constraints onto the protein. So there's additional information regarding, you know, the sort of the state of the pose that's not necessarily just the three-dimensional coordinates. I think that the three-dimensional coordinates are a large portion of the state of the game, but I think there are some of those additional information that's sort of relevant to gameplay.
But is everything pairwise?
I think most of things we're doing are pairwise as far as the score function goes. Okay. I don't know if that was the question, was as far as the score function pairwise. I think we typically use just standard Ref 2015.
Okay.
I don't know if some additional experimental terms like, you know, electron density for those sorts of puzzles. But typically it's just standard Ref 2015.
Yeah, I think that's, I have no authority to speak anything about folded with something like this, but I'd be very interested to see if somebody does try that. I guess just diving a little bit or catching back up. Okay, so we used robots to create XCNet. We showed that XCNet worked well on proteins. We were also curious, I still don't really have a great explanation for why XCNet can go deeper than ECC. And for us, if you look really closely on the y-axis, the loss is slightly lower. So for that was the main outcome that we liked, but we just didn't expect the deeper pattern. And we tried to see why that was the case. So we went back to robots. And forgive me for like adapting a larger figure for something like this, but we're showing the same data as before. So the the validation loss for ECC and XCNet. So this is the same as before. The difference is within each box, the left and right has the unnormalized data being input and then the normalized data input, which I mean, I don't think we ever would have spent time training models with unnormalized inputs with proteins, but since it only takes a few hours on robots, we tried it. So and again, for context, ECC is the standard graph convolution with edge attributes that we're hoping to replace. And it turns out when you have unnormalized inputs, which nobody nowadays does, but when you do, ECC takes this huge performance hit, really bad. In fact, let's see, this horizontal line is just if you have no edge convolutions and you just memorize the most common moves. Or let's see, there's no message passing. So, well, it's essentially the worst you can reasonably get while even trying a little bit. And the XCNet, for some reason, if you have wildly off normal data, really doesn't, it's basically the same distribution in performance, which is kind of a useless superpower, but it might give us a hint as to why XCNet can go deeper. Like maybe when you stray between layers like 2, 3, 4, 5, away from normalization, ECC just throws up its hands and gives up, where XCNet can handle it better. But you know, this is one of those things where, you know, this is all robots data. So it allows us to test things that we would never waste CPUs on otherwise. In terms of next steps, like we're still learning from robots. One thing that we'd like to do with GCNs, especially with proteins, is represent negative space. So for example, if you think back at how we represent proteins as graphs, there's really no way to explicitly represent a binding pocket other than just stating the residue surrounding the binding pocket and hoping that the convolutions pick up that there's nothing taking up the space where we'd like to bind. So it's all implicit, and we'd really like to explicitly point out where there's space that we want to interact with and learn what space matters. And the same is true for robots. So when we move our human behind this explosion and it becomes safe, you know, because all these other robots just run into the explosion, we implicitly need to learn at the moment that if I'm standing right here, there's no robots that can hit me without first going through the explosion. But there's no explicit representation to say that you know, there's a lack of robots up here. And so I think in the future, we would like to have the network, you know, you can think of ways to do that as input and, you know, tell the network and predict what space is useful to know, but we'd really like machine learning to learn what empty space is worth considering. And the other major future direction is reinforcement learning and derivative-free optimization in general. I mentioned before, you can train the entire model to just predict my moves. And then after the fact, do the slow operation. So reinforcement learning is, you know, AlphaGo or DeepStack or, you know, whatever the thing was that learned how to play chess. I'm blanking on that name. And, you know, learning how to play games where you don't really have a strong gradient or any gradient often that can tell you how to update your thousands of parameters or tens or hundreds of thousands of parameters. So this is really slow. And what we'd like to do is just train a model to predict what Jack would do, and then just freeze most of it and then unfreeze a subsection to, you know, sorry, to undergo reinforcement learning. And so one thing that is not obvious that we would like to learn is, well, what region of this network do we want to unfreeze, right? Do we freeze the early convolutions and unfreeze the entire final graph convolution? Or maybe we freeze all of the message construction sections, but then we unfreeze the propagation for all of the convolutions. Or maybe it's sufficient to just freeze everything and just relearn the attention mechanism. And maybe that's sufficient to just learn how to play the game better, because that would be a really low parameter space. That's probably in the hundreds or low thousands of parameters that we would need to relearn. So it would be more economical, and maybe it'd be sufficient to get meaningful improvements. And the hope is that, if we can do this with robots, then when we're modeling proteins, let's say we have a GCN that docks a peptide, or I fall back to peptides for my examples because that's what we use. But, you can train a GCN to reproduce a docking outcome or molecular dynamics as the first pass, and then you freeze most of it, and then you would unfreeze that GCN to learn the better way, instead of just reproducing something quickly, actually learn an improved method for changing your protein. And so I'm highly optimistic that if we do this with robots, we would at least learn from an architecture perspective, what are the fruitful points of this message passing architecture that you can quickly and economically retrain and get the most out of it. But this is the dream. Let's see, everything after this is extra, and we are near the end of the hour. So